now. Here we go. So wait another minute or so to get started. Okay, welcome folks. This is the third GNN user group workshop. And today I have the honor to invite Dr. Marinka Zitnik and also Ke-Xing Huang to come in and present their research work, which is the Therapeutics Data Commons, machine learning data sets and tasks for therapeutics. Later, we will have Dr. Xavier Branson from Nanyang Technology University to do a presentation in about 35 minutes or so. And with that, I'll hand it over to Marinka.
Okay, hello everyone. Thank you so much, Wenming and Grace, for inviting us. We are delighted to be here today, and we will talk about Therapeutics Data Commons, or TDC, which is a new initiative to facilitate machine learning advance in the area of therapeutics. And this is joint work with a number of collaborators, including a rising star student, Ke-Xing, who is here with me today. And today's presentation will be organized into two parts. In the first part, we'll talk around 15 minutes on the design of TDC and what TDC is about. And then Ke-Xing will give a demo of Therapeutics Data Commons. And the website for TDC is tdcommons.ai. So you can already go there and check and see and learn about what Therapeutics Data Commons is about. So let's begin. The motivation for Therapeutics Data Commons really stems from the observation in drug discovery and development, which is one of exciting application areas that has driven lots of research and advances in graph neural networks over the last few years. And so very briefly, the development of a new drug completely from scratch is extremely resource intensive and expensive process that on average takes between 12 and 16 years and can cost from $1 billion to $2 billion to bring a new drug that is safe and effective to the market and design it really from scratch. And so the reason why that is the case, among others, is that the entire process is very complicated. It consists of multiple phases and steps. And so while we might initially start with a number of molecules that are candidate drugs, through multiple steps from the design, preclinical, clinical research, and finally FDA review, we slowly prune away and filter out those candidate drugs that are not safe or efficacious for patients. Now, in each of these steps, there are many opportunities for machine learning in order to accelerate and expedite this process and make it more efficient. So I'll just give one particular example of what I mean by that. And so this is a study that we've been involved in the last year, and it was the result of a task force group formed in Boston area between Harvard, MIT, and Boston University in identifying promising therapeutic opportunities for COVID-19. And what I will describe is very briefly, it's a study where we went in 3 months of time between March 2020 and June 2020, from really collecting the data sets, training GNN models in order to identify what drugs on the market might have therapeutic effect for COVID-19 patients, and then test those drugs in vitro with experiments in lab. And so that has been extremely successful in terms of performance that GNN methods have achieved. So today, unfortunately, I don't have the time to talk about what are the new algorithms that we have developed for this problem. But this slide in particular is showing how predictions made by GNN methods have been substantially better in identifying promising therapeutic opportunities than more classic methods for the problem of drug development and discovery, in this particular case, repurposing of existing drugs for COVID-19. And so this is shown by this ROC curve on the left slide, where better performance indicates methods that are in the top left corner, and the particular 4 pipelines in that space, A1 to A4, are all GNN-based methods using some of the algorithms that our lab has recently developed. So why that is exciting is because predictions made by these methods have enabled to very quickly obtain high quality predictions and validate them in the lab. And so with predictions driven by these methods, we were able to compress years or months of work in days. And in particular, in this case, our collaborators from National Emerging Infectious Disease Laboratories have then took our predictions and compounds that were predicted by the model and screened them for efficacy in African monkey cells and then human cells. And this looks very interesting for someone who is a computer scientist, because this is how wet labs look like, almost like some kind of space environment. And the result of that was that was a finding of 77 drugs that had strong effect in terms of inhibiting viral growth across broad range of concentrations. And importantly, for those who, for the ML folks in the audience, is that that result is an order of magnitude better and gives us an order of magnitude higher hit rate among top ranked drugs than what was possible by prior work, which was either brute force experimental work in the wet lab, or it was or was driven by more traditional machine learning methods. It also led to discovery of new class of drugs that we call network drugs, but I'll not go into that today. But this is just an example of how machine learning driven methods, or in this particular case, GNN methods, can really expedite and accelerate development of safe and effective therapeutics. So therapeutics are really an exciting application area for machine learning, but there are some challenges. So data sets in this space can be of very different types, and they are often scattered around biorepositories. And for those researchers who don't have relevant domain expertise, it's very challenging to identify, process, curate data sets that are relevant to a task of interest. For machine learning researchers, it's often very hard to identify what data sets to use because they are scattered around repositories and there is no centralized data resource for a variety of questions that exist in this space. And because of that, the use of current machine learning models in practice is relatively limited. So they're really not routinely used in everyday clinical practice or real-world deployment. And so there are many opportunities to make this happen by really addressing the challenges that are shown in this slide. So the question that we are concerned with here is really what can we do to facilitate algorithmic and scientific advance in the area of therapeutics? How can we advance machine learning for the area of therapeutics? And so for that, we have developed an initiative that we call Therapeutics Data Commons, or TDC, which is the first unifying framework that allows us to systematically access and evaluate machine learning models across the range of therapeutics. TDC currently includes, in the first initial release, 77 machine learning ready data sets that are spread across 23 different kinds of machine learning tasks that cover the entire process of drug discovery and development. And TDC comes with an ecosystem of tools, libraries, leaderboards, and community resources. So this is unpacked a bit in this busy slide, where it shows on the left what is a typical life cycle of machine learning for the area of therapeutics that starts with First, formulating a meaningful machine learning task, meaningful from the standpoint that it can really lend itself to actionable hypotheses in experiments and really accelerate drug development. Then to identification of relevant data sets, developing models, evaluating performance of those models, and comparing them to state of the art. And so for each of these steps in the life cycle of therapeutics machine learning, Therapeutics Data Commons provide a very rich set of tools and structures that include support functions in terms of meaningful data splits, molecule generation oracles, variety of processing helpers, as well as metrics for calculating performance of different models and comparing those performance in a fair and unbiased way, which all can be visualized through leaderboards, which TDC includes as well. So on the core, TDC is organized in 3 tiers. So the way we think of machine learning problems in the area of therapeutics is the following. We can roughly classify any problem that we encounter into one of 3 groups. And so we call them single instance prediction, multiple instance prediction problems, or generation problems that are primarily concerned with either predicting some form of property of an individual entity, might be a single molecule or a single protein or a single compound, or we might want, or we're concerned with predicting a property of a set of objects or multiple instances, which might be a combination of drugs or a complex of proteins. And the third kind of problem, the third type of problems are problems that are concerned with not predicting properties of objects, but really generating certain objects that are of interest for drug discovery and development. And so that is broader than simply generative modeling, generative class, a class of generative models, which we call then the 3rd generation problems. So in TDC, for each of those 3 problems, we define a set of learning tasks. And for each of learning tasks in the 3rd tier, we have a set of data sets. All of them are machine learning ready data sets with predefined training, validation, and test splits. And so that means that now we can take the 64 data sets and spread them across those 23 learning tasks and across 3 different types of problems that we are modeling in therapeutics machine learning area. So TDC, as I mentioned, includes a variety of data processing and split functions. And Kishin will later do a demo of some of them. This includes metrics for calculating performance of the models. Some of them are well known in machine learning. Some of them are domain-specific metrics for drug development and discovery. A variety of data splits, not only random, but also scaffold splits, cold start splits, combination splits, and data processing helpers that can help model developers and machine learning researchers understand better their models, audit them, and debug them. An important part of supporting functions are also molecule generation oracles that are provided in TDC and allow users to test the quality of generated objects, such as the quality of generated molecules, against a set of oracles that are a priori defined based on the domain knowledge of biology and chemistry in order to get sense into how good molecules currently can, how good current models can generate these molecules. So before I give the floor to Kishin, I want to make one step back and kind of talk about what are the opportunities that TDC creates for graphs. So TDC data sets are not necessarily limited to graphs, but we have seen that graphs are extremely important way of representing data relevant to drug development and discovery. And so TDC creates fundamentally new opportunities for graph structure data. So much of current efforts in graph representation learning for drug development has really focused on small molecules, But there are many other types of therapeutics out there, and their data sets for them are also provided in TDC. So we hope that that will stimulate some of new algorithmic and methodological development for these different kinds of therapies in a similar way, as much of graph level representation learning has really been driven by advances for molecular graphs. And secondly, there are a variety of different types of data sets in TDC, and those that are graphs can be graphs that are very different or diverse and complex in many ways and rich. This includes both graphs that represent genomic sequences and relational structure on the level of genomic sequences, molecular graphs, protein graphs, graphs of interactions between individual cells in human body. And these could be graphs that really have billions of nodes representing just a small sample of the number of cells that are in human body, including gene co-expression networks, finally knowledge graphs. So lots of opportunities for graphs, and we really encourage those here on the call who are actively working in developing, designing, implementing, using GNN or more broadly graph representation learning methods to check out TDC. It's an open science initiative. We very much welcome contributions from the community, both in terms of defining new data sets, defining tasks, and contributions to our leaderboards. And I want to highlight a group of fantastic students who are really working on this on a daily basis to make TDC grow and shine. And so now I will give the floor to Kishin, and he will show a demo of TDC.
Cool. Sounds good. Let me share my screen. Can you guys see the screen? Okay.
Yeah, we can.
Awesome.
Perfect.
Okay.
Thank you.
Okay. Awesome. So yeah, so next I will showcase a demo which will kind of run through some of the functionalities Marinka just talked about, and then through the TDC library. So first I want to highlight our website, which is tdcommons.ai. And then it documents lots of the useful information about data sets, tasks, data functions, and also leaderboards. And it will also become very, very handy when you write the code on using the TDC library. I'll demonstrate that. Okay, so let's get started for the demo. First, to install TDC, it's very easy. You can install it through pipe. And then the core package is very requires very minimal external dependencies, so it won't create the kind of version conflict and things like that. Okay, so next I will talk about how to access the data sets contained in the TDC. So we provide kind of these 3 lines of code data loaders for 66 data sets in 22 tasks. And then we leverage this kind of tiered structure Marinka just said. So for example, want to retrieve the data set HERG from the toxicity task under the single instance prediction problem. You can just specify the machine learning problem and then the therapeutic task and then the data set name here, and you will get the data loader. So this kind of format would can work for all the 66 data sets in 22 tasks. And this information can also be found on our website. So for example, want to do HERG data set in tox and a single instance prediction problem, you can go to the data sets tab, and then you get the single instance prediction and the toxicity machine learning task and the HERG blockers data set. You will see the data set description, like what does that mean in a easy to understand language, and the task descriptions, data set statistics, and some available splits for this task, and also reference and data set license. And you can copy paste the code here to retrieve the data. So the output of these 2 lines of code is the data object, which contains lots of functions to retrieve data set, and also some utility functions, which I'll talk about later. So to get the data set, simply call the get data, and then you will get the machine learning ready data format. So this is like the most clean format possible, because so there's no fuzz, and it just specify the drug like the smiley string, which is the most basic format for a drug, and then also the label for this drug. And then this data object, you can use like various utility functions. So for example, you want to get the split, simply call get split function on the data object, and then you can specify the method, splitting method. Here we use a scaffold split, like seed the random seed, and also the fraction for training, validation, and the test set. And then it will return a dictionary which each contains the splitted data set. Cool. So that's some showcase some like the most basic usage of TDC data loaders, and that applies for the single instance problem. So similarly to that, to retrieve a data set in the multi-instance problem, you can also go to the dataset tab here, click multi-instance prediction dataset. You can explore here. Like each task has this kind of task description as well, and also the dataset description. So here, for example, I want to retrieve the GDSC1 dataset from the drug response prediction task. You can just click the drug response prediction, get the GDSC1 dataset section, and then just copy paste the dataset here. And then it will also generate the most machine learning ready dataset format. So for drug, we have the smiley string. For cell line, we have the gene expression profiles. And then also the label, which is the drug response for that cell line. And similarly, so that's for multi-instance and a single instance prediction problem. Similarly, for the generation problem, you can also do the same, simply replacing this this code here with the name generation and the specific machine learning task name. So here I want to show, like, if I want to get the USPTO 50K data set for Richard synthesis prediction task, you can just go here and then here, and then just get the data set, which is also the most like machine learning ready format. Cool. So hopefully that gives a sense of what is the kind of basic usage for TDC data loader, which is like very easily to retrieve this data set and the task in organized manner. So next I will showcase how to some of the data functions. So so we also have in the website, we also document each of the data functions. So Marinka said about model evaluator and also the dataset split, which I also somehow demonstrated before. And then I want to highlight three functions that are relevant to the graph machine learning community. So first, we know that for the small molecule drugs, we can represent it as a graph. And then we provide this useful function called a molecule converter, where you can specify the destination format to transform it using one line of code to transform the biomedical representation to the machine learning representation that you want. So for example, here I showcase you can directly transform from the smiley string to the DGL graph format just using this one line of code. And similarly, this function is also supported in the data loader, where you can add a convert format parameters and specify the format name, and then you can get the data set with an extra column with the DGL graph object, and then you can apply your favorite DGL model on top of it. Cool. And another example is for data processing helper is for multi-instance prediction problems such as drug target interaction prediction. We can sometimes we can formulate it as a network link prediction problem, where we have a network of drug and target and entities, and then we will want to predict the missing links, which corresponds to the potential drug target pairs. So we also provide some basic the data processing helpers to transform from the raw tabular data format to the graph format. Here I demonstrate from the data object, you can call it the toGraph function, where you will get the data, the DGL graph object, where you can directly apply your machine learning models. So another big category is molecule generation oracles. So we provide 17 oracle functions, and noted that this molecule generation can be formulated as a graph generation problems, where you want to generate new graphs, molecule graphs that has some desirable properties, and these properties are measured by the Oracle functions that we provided. So we've had many realistic ones. So here I want to showcase this one. Is called synthetic accessibility, which basically measures how accessible is the generated molecules. So you can specify the name of the Oracle with the Oracle class, and then just simply feeding the smiley string, it will return the Oracle value for each smiley strings. And then this one would like this value just correspond to how accessible is this drug. Cool. So hopefully that gives a taste of the data functions the TDC supports. There are many others. Feel free to navigate to explore on the TDC website. So next and last, I want to demonstrate the TDC leaderboard. So TDC leaderboard is a place for you to submit your state-of-art models to compare with others, and then the result, and we design the leaderboard in a way that the performance on the leaderboard would directly kind of translate to like a more like realistic therapeutics impact, basically. So here we also provide a very easy to use kind of class called benchmark group, which will help you to run the to run your model on the leaderboard. So here I want to demonstrate on using kind of like a message pattern neural network to predict ADM properties and submit into the TDC ADMET benchmark leaderboard. So the first step is to load the benchmark dataset. You can call from TDC import benchmark group, where you will get like a collection of benchmarks, which all center around this ADMET theme. And then you can get the specific benchmark that you're interested in. So for example, here we're looking at this Kakao21 leaderboard. You will get the group.get Kakao21, and then this one will contain useful information such as like the fixed training validation and a test set data. And then the step 2 is to train your model with 5 rounds. So we use here as a demo use a depurpose, which is also a framework that we developed for encoding compounds and proteins. So here we use drug encoding, which is MPNN to encode the drugs, where you will simply get a for loop where each seed would specify different training and validation split, which will get the training and the validation files. And then you can just replace the line here with your machine learning model, and then just feed in the data set and generate prediction on the test set. And then you can just append this test set on our prediction rounds, which is like to store it, and then just evaluate it using the benchmark TDC benchmark group function, which is .evaluate many, and then it will return the submission ready format, which here is the standard like the mean and the standard deviation, and then you simply copy paste the result and submit to this form, and then your result will be reflected on TDC leaderboard website very soon. So we can see here like the TDC like all of these leaderboards can like far from perfect, like the performance, and there are so many opportunities for algorithmic innovation. So please submit your state-of-art models to TDC leaderboard. Cool. So that wraps up my demo. So please visit our website, start our GitHub repo, and then also join our Slack workspace. And then you can find this notebook at our GitHub repo as well. Yeah, thanks.
Thank you, Cushing. Thank you, Marinka. Any questions? So we have 5 minutes for questions. You can just unmute yourself and ask the question, or you can put it in the chat window. I'll be happy to announce it from there as well.
I have a quick question about your data sets. I was wondering if this is meant to be something like for testing the methods mostly, or this is something that is being updated regularly. For example, for protein-protein interaction networks, like maybe every couple of years, there are some new data, for example, on a Strings website. Do you update your data regularly, or as I said, this is for example, for testing, initial testing of the methods?
Yes, so that's a great question, Ellie. Each of the data sets have a provenance tracker, so it's always possible to track it back to the primary data resource. For example, you were mentioning string DB, which would be then a particular version of string database at one point in time. The main goal of TDC is to provide an ecosystem for testing performance of algorithms in a way that reflects challenges and meaningful tasks in drug development and discovery. So it is primarily designed for algorithm development, testing, and evaluation in such a way that would then translate to real improvement in performance in practical domains. That's why we are putting lots of effort into defining meaningful splits, meaningful molecule generators, benchmark groups, and so on. So the data sets would be are updating over time. Now TDC is relatively young initiative, so so far very few data sets have been updated over the last few months, but as they will get updated over time, we will include them into TDC, their updated versions as well.
Thank you.
Yeah, there's a couple more questions in the chat window. Is it using methodology that on the link prediction or graph classification? And the other one is, have you used models available, predictive or generative from DGL in this data set?
Yeah, so let me answer first to the question of Noor. So TDC is not a library of ML models. The main goal of TDC is to provide data sets and task definitions and frameworks so that you can test your models that you design, invent in DGL, Python Geometric, any other TensorFlow PyTorch library, and you want to test them against data sets and tasks for therapeutics development. So we provide some baseline implementations for some tasks and initial performance across leaderboards, and for that we use some DGL models, also some models that we have recently developed over the last few years. Another question is it what kind of methodology is TDC using? So TDC groups those 66 data sets into 3 different problems. You can sometimes and those are prediction problems that relate to predicting properties of individual entities. Sometimes that corresponds to predicting properties of nodes, which would be classically node classification, but not always. That's why we define that as a problem of that is concerned with a single instance prediction, and then multiple instance prediction. In the case where we're predicting properties of 2 instances, that would be link prediction, but generally it is not. And in many tasks in therapeutics are concerned with predicting much more than just links. And so that's why there is this group of data sets and tasks in TDC that are then called multi-instance prediction problems, and then finally generation problems. Just again, to summarize, TDC provides a framework with data sets, tasks, loaders, evaluators, so that you can test your own models, how well they perform very easily, and kind of be sure that you work on high quality data sets and meaningful data sets, even with little background in biology or no background in biology or drug discovery. So.
Any other questions? Okay, well, thank you again, Marinka and Cushing, for your presentation. So our next presenter is Dr. Xavier Branson. He's going to be talking to us about the transformer network for traveling salesman's problem. And he is from the Nanyang Technological University. And here's his presentation. Hi, Xavier. Are you able to get the mic working?
Okay.
That works.
Can you
now.
hear me?
Perfect. Yes, we can hear you, but we don't see your screen shared
Yes.
for some
let me do
reason.
that.
I'll let you share the screen, and then I'll go off mic.
All right. Can you see the slides?
Yes, we can.
All right. Perfect. Welcome, everyone. So thank you, Wanming, for the introduction. And since I have the opportunity, I also would like to congratulate the DGL team, for its outstanding work to make graph networks accessible to everyone. So I remember personally how tricky it was, a few years back, and now it has become, easy, fast, and reliable for everybody. And I also would like to say that I'm very excited that NVIDIA is working on making sparse linear algebra optimized for GPUs. This is something the GNN community is very welcome. Okay, so I'm going to talk about the transformer network for the traveling salesman problem. This is a joint work with Thomas Laurent from LMU. This talk is a bit different from the great talk of Marinka and Keishing, but I think also it demonstrates the flexibility of graph neural networks to tackle different problems. Okay, so this is the outline. Since I have 30 minutes, so I'm going to be brief about. Let me do that. Yeah, about history of TSP and traditional solvers. Then I will talk about the recent neural network solvers, what we propose for this problem, the decoding technique, the results, and finally some discussion and conclusion. So the TSP problem, so this is probably something that you know, but just to be sure, we are on the same line. So you have a list of cities, and what you want to do is to find the shortest path that go through all cities exactly once and come back to the original city. And this problem was, formulated a long time ago by William Hamilton in the 19th century. And this problem actually belongs to a larger class of routing problems that are used every day in industry, like warehouse organization, transportation, supply chain, hardware design, manufacturing. So TSP is NPR. It means that the complexity is factorial. But this is also the most popular and the most studied combinatorial problem, starting with the mathematician and father of informatics, von Neumann. So TSP has driven the discovery of several important optimization techniques along the years. Traditional solvers. So the traditional ways to tackle combinatorial problems are you can use exact algorithms like exhaustive search or dynamic programming or integer programming. So these algorithms are guaranteed to find the optimal solution, but they become intractable when n gets larger. And then you have approximate heuristic algorithms. So you are going to trade exactness with computational efficiency, and they are problem specific. So you are trying to design some heuristic that you apply iteratively until you get to a solution, an approximate solution. So these algorithms have polynomial complexity, and we characterize, their quality with respect to the optimal solution. So I'm not gonna have time, to go through this. But just to tell you, so exact algorithms are dynamic programming. So you go from factorial to exponential complexity. Then you can use integer programming technique. So Concord is very highly specialized integer programming with cutting planes and branch and bound. And Concord today is seen, as the fastest exact TSP solver for large instances. Okay, so the way you formulate the problem is, an integer linear programming problem. So you see here the linear objective, and then you have some linear constraints. And the thing, you cannot solve directly this problem because the solution that you want is non-convex. So what you need to do is to relax the space of solution to continuous solution. And then suddenly you can solve problems which are classic, which are called linear programming. So this goes to, cutting planning techniques. And then the thing is, when you use linear programming, the solution that you get is going to be continuous. So you would like to come back to the discrete world. So when you do that, then you will need to use branch and bound to be able to find optimal solutions. So the overall complexity of Concord is going to be the complexity of solving an LP problem, linear programming problem, and then the complexity of the number of branches that you need to do to get to the solution. So it's not mathematically, we don't know mathematically, the number of branches that you need to get, that you need to solve to get to the solution. So what I did, is just to look at, when n, which is the x-axis, and the y-axis is the time that you need to solve, TSP solution with Concord. So the Concord complexity is in dark. And here what I did is that I tried to, look at the polynomial complexity. So when n is small, larger than, smaller than 1,000 nodes or cities, then Concord is polynomial. But when we get, to larger number of cities, like 1,000, then the complexity becomes exponential, which was expected. Okay, then you have, approximate algorithms. So basically, you are going to use some approximation of other algorithms like the minimum spanning tree. You can use also a technique like insertions, so the idea, for example, here is to insert, the city which is the farthest from the current solution, and you do that repetitively. Then you have Google OR tool, which applies different heuristics to get to the solution. Then you have to opt algorithms. So the idea is you want to swap, a certain number of edges to reduce the length. So this is 2 edges, this is 3 edges. LKH, tree algorithms, is the best heuristic, algorithm for solving TSP, and it is based on this idea of, 2 opt and 3 opt moves. So if we looking at, the hierarchy of traditional solver with respect to exactness, with respect to the solution and complexity. So exactness, of course, you will get something which is exact, but the complexity is going to be higher. And when you start, relaxing the solution, then the complexity gets better, which is expected. Okay. So let's now see the neural network solvers. So deep learning, we know, has significantly improved, computer vision, natural language processing, speech recognition in the last decade by replacing, handcrafted visual text speech features by feature learned from data. So for combinatorial problems, the main question is, we can also use deep learning to replace human engineering heuristic by, learned heuristic. And this is very appealing because developing techniques for NPR problems can take quite some expertise and a number of years. So for example, TSP has been actively studied for 70 years, by great mathematicians and great computer scientists. And there are many problems today that are combinatorial by nature, especially in industry. So the last 5 years has seen, many works, trying to tackle combinatorial problems using graph neural networks or neural networks, and have been, capable to get, preliminary, very promising solutions to this problem. So let me review quickly, these neural network solvers. So the first one, which was a long time ago in 85 by Hopfield. So there was the first neural network to solve small TSP. And then more recently, so there was the work by Oriol Vinyals and his co-author. And that was really, I think, the pioneering paper, that uses modern deep learning to tackle TSP. So everything started from there recently. So the idea was to use, was to encode the cities, by using a recurrent neural network, and also the same also for decoding city. And then they use the attention mechanism, to know what is going to be the next city to visit. So this architecture is actually has been successfully applied in NLP, you know, by Badano, Cho, and Yoshua Bengio for machine translation. So that was, you know, the precursor of transformers. So the idea was to use, you know, the attention mechanism. It was a powerful, you know, mechanism. And here it was used for combinatorial optimization. Then there was, you know, improvement of the pointer net work by Sami Bengio and his co-author. So in the first work, the learning was done by using approximate TSP solutions. So it was a supervised learning framework. And in this following work, the idea was not to use any TSP solution, but just, you know, use reinforcement learning to learn a policy that would provide TSP solutions. And the award here is just the tour length. You want to minimize the tour length. In this work, so it also improved the original pointer net. So in the original pointer net, the recurrent network that encodes the cities, you know, has some constraint about the order of the city. So this makes sense for NLP, but it doesn't make any sense for TSP. So the order of the city is completely irrelevant in this case. So you want to have an order invariant or permutation invariant, you know, encoder. And this is what was done, you know, in this work. Then in the work of Song and his collaborators, so they use reinforcement learning and they estimate a Q state functions to know what would be the next node in the tour. Okay, and they use also memory replay and intermediate rewards that, you know, encourage fastest node insertion heuristic that we know is a good heuristic. And there was also the work by Joan Bruna about casting the TSP as a quadratic assignment problem. Here they use the graph neural networks to learn a policy by supervised learning. Okay, then there was this work by Comfer and his co-author. So they solve a variant of TSP by using multiple salesmen. And they train by supervised learning, and they actually got, you know, a fractional solution, so a continuous solution, which was transformed into a feasible solution by beam search. So interestingly, it's a non-autoregressive approach. So the previous approach was autoregressive. It means that you are going to decode cities, you know, one after another. Here you do everything, you know, in one step. Then there was the work by Louis-Martin Rousseau and his collaborators. So the idea was to use a transformer to encode the input cities, and then using actor critique reinforcement learning to decode the tour city after city. And the solution was refined, you know, by a two-opt heuristic. Then there was the work by Kuhl, Van Hoof, and Max Welling that also use, you know, a transformer to represent the input cities. And they use, you know, for the decoding, a query which is based on the first city, last city, and a global representation of all cities. In this work, we basically use a deep graph neural network, and we learn by supervision by using Concord solutions, you know, the probability that an edge belongs to the TSP solution. And we basically decode by using beam search, and it's a non-autoregressive approach. Then there was this work by Hu and his co-author that the idea was so you can learn to do the two-opt algorithm. So in the original two-opt algorithms, this is where you swap, you know, edges. So when you do that, you know, it's going to take a lot of time, a lot of moves to get to the solution. So you can use actually reinforcement learning to learn which edges you want to move. Then there was, you know, this paper by Xing that was, you know, using graph neural network with Monte Carlo tree search. So the standard way to do decoding is to use, you know, beam search, but you can improve that by using Monte Carlo tree search. So that was inspired by AlphaGo. And it's a good idea because when you make a decision, you know, you cannot go back. So here you would like to look at, you know, ahead to be sure when you make a decision. Then more recently, there was this work that combines supervised and reinforcement learning. So they use the first step that use our model to know the probability that an age belongs to the solution. So that was done by supervised learning. And then they have the second step that decode, a feasible tour by using reinforcement learning and Monte Carlo research. Interesting, they went to larger TSP size by using some, graph subsampling technique, and they were able to get, a very good solution for large TSP size, 200, 500 to 10,000. Also recently this year, so there was the supervised learning technique plus dynamic programming developed by Kuhl and his co-author. And they also use, the supervised learning technique that we developed to learn an age probability map. And then they use dynamic programming to decode feasible solutions. And they get the best supervised learning solution for 100. So now let me introduce our proposed architecture. So we're going to cast the TSP problem as a translation problem, where the source, the input language is going to be a set of 2D points, and the target language is going to be the tool, so a sequence of indices with minimal lengths. So of course, the motivation is transformer has been very successful for natural language processing. So let's try also to apply this to combinatorial optimization and see its performance. So we train by reinforcement learning, we train by reinforcement learning by using the same setting as Kuhl and his co-author. And the reward is basically the tour length. And the baseline is going to be simply updated if the train network, improves on a set of TSP. So this is a proposed architecture. So we have an encoder, then we have a decoder. I'm going to describe them. So for the encoder, we are going to use a standard transformer encoder. So here you just have a single head where you have, the attention map with the query, the key, and the value, which are based, on the 2D coordinates of your input cities. And then we have an extra token here, which is going to be helpful, to start the decoding process. So it's like fake city doesn't exist, but it's something useful to decode, to start decoding. The only difference with the standard transformer is that we don't use layer normalization, we use batch normalization, which gives better results. So it makes sense because here you train by batch of same graph size. So you can basically use batch normalization. It's going to speed up and improve the accuracy. So we start, with our input cities, and then what the encoder is going to do, hopefully, is going to give us, better representation of the city in such a way that the decoding process will be, easy to do. Okay, so this is deep learning. Deep learning is trying to find the best possible representation such that the next step would be easier to do. So we just use, self-attention layer. For the decoder, so it's going to be autoregressive. So we are going to decode one city at a time. So let's suppose, for example, that we have decoding the first T cities in the tour, and we want to predict the next city. So to do that, we are going to have 4 parts in the decoding process. The first part basically is going to if we have the time T, the input of the decoder is going to be the encoding vector for the city that was predicted in the previous step. Okay, so we get here IT, and this is going to be the input of the decoding process. Okay, so we use also a positional encoding to know the order of the decoding city. So we have 0, 1, 2, 3, 4. But if you want to be independent of the length of the TSP, it's better to use the original positional encoding proposed by attention is all you need. So it's a sine and cosine functions. Okay, the second part, once you have the input of your decoder, now what we're going to do is that we are going to make some query by making talk this input vector with all queries in the partial tour that you have decoding so far. Okay, so we want to query the partial tour and give the best possible query for the next node to decode. So for this, we are going to use again self-attention in the partial tool. So this is the equation again for a single head, but we use multi-head residual connection, and we use linear normalization. So here we have one vector to decode at at each step. So we cannot use batch normalization, so we use linear normalization as in the standard transformer architecture. Okay, so we do L decoding layer of self-attention, and then the next step is once we have a query, we are going to use this query to look at what can be the next city in the tour. So we are going to again making talk this query with all cities that are yet to be visited. So for this, we again use an attention layer. So it's the query attention layer. So basically, you are going to talk with the next cities. Here we have a mask of the cities that have been visited or not visited. The last layer is not to use multiple heads. It's to use only one head because you are only interested of the next city. So the last layer is just doing a single head attention. And finally, you will get a probability over the next possible cities, and you are going to sample this probability using Bernoulli sampling during training, and then using greedy sampling. So just taking the index with the maximum probability at inference time, to evaluate the baseline, to know when you're going to update the baseline or not. Okay. So I said at the beginning that we were inspired by, transformer for NLP and translation, but there are some differences between translation and combinatorial optimization. So first of all, the order of the input sequence is not relevant for TSP. And actually, we want the system to be invariant with respect to the permutation of the input city. So this is different from NLP, where the order of the words, is important. So we use for the decoding sequence. So we use a positional encoding because then here for the decoder, the order is very important. So we use a positional encoding like for NLP. For the encoder, we are using batch normalization because again we have a batch of similar TSP size, so batch normalization works better than layer normalization. And for the decoder, because we are working one vector at a time, we use layer normalization. So in the case of NLP, we cannot use reinforcement learning, so we use supervised learning by having a training set, to learn the transformer architecture. In the case of combinatorial optimization, we don't need any training data. We can just learn by reinforcement learning by optimizing, the length of the tool. And finally, both transformers for NLP and TSP has quadratic complexity. You have the n square complexity and the number of layers. So now we can also compare with the most related architectures to ours. So there was a work by Kuhl and by Dedon. So we use the same transformer encoder with batch normalization as well. For the decoding architecture, our query is different. So for us, we are using the self-attention between the new time and all the previous times in the partial tool. In the case of Kuhl, they are using the query based on the previous city and the first city, and also a global representation of all cities. And in the case of Dedon, they are using the query based on the last 3 cities in the partial tool. Also, we start, the decoding process by having, as I say, a token city. So this is something standard in NLP, if you want to do classification of a sentence, so you have, a token for the classifications. Here we use a token to start the decoding process. So Z is going to talk with all cities, and by talking with all cities, he will try to find the best position in the decoding space. So this is different from Kuhl and Dedon. So Kuhl are using random token, and it was also the same for Dedon, but it's this random token was at the beginning of the decoding. So in our case, our token was at the beginning of the encoding. Okay, decoding techniques. So I may not have too much time, so I'm going to be very brief about this. So a tour is represented by order sequence of indices, I1, I2 to IN, and you can cast the TSP, as a sequence optimization problem. You want, to find a sequence which is going to optimize, the probability that the sequence belongs to the TSP solution. So of course, this probability will be here smaller than this one. So when we do autoregressive decoding, there is something which is interesting to do is to factorize the TSP probability by using a chain rule. So the probability of having a tour given a set of 2D points is going to be the probability of selecting the first city given X times the probability of selecting the second city given the previous city I1 and X, and so on and so on. So the decoding process is basically to maximize this objective. So it's going to be the product of the conditional probability, and this conditional probability will be approximated by the neural network that we just described before. Then the decoding. So if you want to do exact search, then you go back to factorial complexity. You cannot do it, so you need to do some approximation. So the one which is the fastest is to do greedy search. So each step, what you do is that you just select the index with the highest probability. The complexity is the order of the number of the cities. And then you can use more advanced, sampling techniques like beam search or also Monte Carlo tree search. And they know that, they improve results for NLP and also TSP. But here you're going to have, a certain number of, exploratory paths. So it's going to be the number of beams that you will add. Beam search is basically, so maybe I'm going to skip that. Numerical results. So let's see, the results for TSP 50 and TSP 100. Here you have the objective. So this is the length, the lower the better. And here you have the gap. So basically you are looking at, the optimality gap between, the solution that you get with respect to the optimal solution. Here you have the total time to process 10,000, test TSP. So this is fixed for all models. Okay, so we have 10,000, TSP 50 and 10,000 TSP 100 for the test set, and IT is for inference time. So you would like to compare, how much time is going to take if you have one TSP. Here you have different techniques. So this is mixed integer programming with Concord and Jurobi. Concord is again, the best technique available today. So it gets, the best objective. So the gap is 0%. Then you have heuristic techniques. Again, the best heuristic techniques is LKH3, which also gives you optimal solution. Then here you have learning techniques. So you have supervised learning, SR. So the first technique, again, developed was the pointer net by Oriol Vinais and his co-author. Then we did supervised learning in this paper, and then more recently there was Kuhl and Maxwelling doing this work, so they got result almost optimal, with respect to Concord. There was also recently a work that combines supervised learning and reinforcement learning by Fu and his co-author, so they get also very good results for TSP 50 and TSP 100, and they also good results, for larger size. They try to 10,000 cities. In these two situations, the algorithms are going to use the Concord, algorithms to generate exact TSP solution to do the supervised learning. So if we look at reinforcement learning here, they don't use any training TSP solution, just to trying end-to-end to learn an algorithm that would generate, the TSP solutions. So there was work by Bello, by Dai, Dedon, also cool, Shin, Wu. And then what we get, in the case of reinforcement learning, we get, something very close to the optimal solution for TSP 50, and something which is also close to the optimal solution for TSP 100. Okay. Yeah. So something also interesting is that so neural network can be quite, I would say the number of lines that you need to code neural networks is quite small, which is also quite interesting. So we release the GitHub code here. So for some visualization, for fun, so this is the solution given by neural network, and this is a solution given by Concord. Okay, so you get interesting solutions. So here, for example, the two solutions are very close to each other. This is also, you also would like to do zero-shot learning. So you train on TSP 50, and then you try, when you double the size, TSP 100. And you see that, so the performance is also quite reasonable. Yeah. We also, of course, compare the experimental complexity, of neural networks with respect to Concord, and we know that. So we have a polynomial complexity, and then we have exponential complexity for Concord. Okay, now discussion. So in this work, we essentially focus on the architecture. So like, natural language processing, computer vision, where transformers are doing a very good job. We can also see that transformer architecture can be successful to solve combinatorial problems. And not only TSP can apply to many other combinatorial problems. And it also improves, the recent learn RL, so reinforcement learning heuristic, when we don't use any TSP solution. Further developments can be, we can improve the sampling techniques. So people use group beam search, to increase the diversity of beam search, and also Monte Carlo tree search, which is also which improve results. We can also use some intermediate rewards by using to opt, heuristic. It has shown, to improve results. But something that I want to emphasize is that we should be very careful. So the traditional solvers like Concord or LKH, they still outperform, the neural network solvers in terms of performance and generalization. So neural network solvers are faster than the traditional solvers, but we are not yet the same performance. So what's next? So we can learn, longer, because differently from NLP, with combinatorial optimization, you can generate, an infinite number of training data, but you don't want to do that for too long. We can improve the architecture, the learning paradigm. And then the next question is, of course, to scale to much larger size. So if you use transformer, you have the bottleneck of quadratic complexity. Now there are several works, going to linear complexity. And there's also this recent work by using graph subsampling techniques that looks also promising to scale to larger TSP size. Something else also that would be interesting to do is to consider harder TSP problems. So TSP is the, is like the MNIST task of, routing problems, but you can consider much harder problems of TSP with Windows constraint, for example, where traditional solvers can only provide, weak solution, or they would take, very long to solve. Something else that we can do is, again, to look at more, harder combinatorial problems, where, so if you look at, Jurobi, it's a generic, integer programming solver. It can do linear and quadratic objective with convex constraints, but now it cannot do non-convex objective and non-linear constraints, something that you can do with, reinforcement learning and neural networks. Another, alternative taken by research group, by other research groups, is to use, learning techniques to improve traditional solvers. So, for example, one of the core technique in combinatorial optimization is branch and bound technique. So branch and bound, the efficiency will be the number of branches that you are going to explore. So there exists, you know, a heuristic to decide which branch you are going to take. And some heuristic, like strong branching, is very good, but is very expensive computationally. So what the work was done, you know, in the recent paper by Lodi and also by Nair, is to you know, learn this strong branching by imitation learning. And then, so it's going to be long to learn for the training, but that at inference time, it will be nothing. So this is a way, actually, they show that they really speed up significantly, you know, branch and bound computational time. So that's very interesting. And of course, the next step would be not to do imitation learning, but to learn, you know, by reinforcement learning, better heuristic. Conclusion. So I think combinatorial optimization is really interesting because it's pushing the limit of deep learning. Traditional solvers still provide better solutions than learning models, but also traditional solvers have been studying for a very long time, and the interest of applying deep learning to combinatorial optimization has just started. So this topic will naturally expand in the coming years because combinatorial problems are, you know, everywhere in industry. You know, assignment, routing, planning, scheduling is our, you know, routine everyday task that you want to optimize. And also there will be novel softwares that will combine continuous discrete optimization and also learning techniques coming. I want to mention that, so very recently, so last month, basically, we organized a conference at the intersection of deep learning and combinatorial optimization. So we have, you know, great speakers, and all videos are now available on YouTube. So if you want to know the state of the art of combinatorial optimization with deep learning, so I will recommend you to watch these videos. And finally, I would like to make a workshop announcement. So it's going to be next month, very soon, you know, machine learning system conference. And in conjunction of the conference, we are organizing with the GL team, with Zhang Zhang and other people, Michael Bronstein, Stephanie Jegetar, George Karipis, and Peter Velikovic. We are organizing a workshop on graph neural network and systems. So I would like to thank you for your attention.
Hello, Doctor. Thank you, Dr. Branson. Hello, everyone. Any questions? And we have another 14 minutes, so very happy to take questions, and we can also talk about other things as well. So.
Hey, Xavier, this is Joe Eaton here. So I manage the cuGraph group for NVIDIA. And we've been working on some traveling salesmen and variations on this for some time now. It's really a challenging problem. It's a tough one. I think Monte Carlo tree search is a really interesting way to look at it. Right now we're just using massive parallelism and 2-opt, right? So if you have a lot of horsepower, you can throw a lot at it.
Absolutely.
But this is really interesting. Thank you for your talk.
Yeah, so for Monte Carlo tree search, which is also interesting, is that it's like AlphaGo. So you can also learn, you know, a policy that will help you, you know, to look at, you know, the better, you know, path to explore for Monte Carlo tree search.
Exactly, right.
So
it's all about
yes,
pruning the search space as much as possible. Yes, yeah.
Absolutely. So I think this is very promising. Because all, you know, the standard techniques based, you know, for software engineering, you know, all these search algorithms, they can be speed up now by learning. So it's going to be, you know, this hybrid algorithms coming, and I think they are really generic as well. So that's going to be quite useful. Yes.
And for these harder variations, like the capacitated vehicle routing problem, I mean, that's where the practical applications are, but they, you know, the optimal solutions aren't even known for a lot of these cases. So it's much more challenging to even evaluate, you know, how close you are to optimal in those cases. So we have to get really good at TSP before we get, you know, really good at the harder ones.
Absolutely. So TSP is a kind of the end list, right? So you want to be good on TSP before, you know, you would like to try ImageNet, for example. So so TSP for us is really a way, to develop some good architecture, some good learning paradigm, and then go into more complex TS routing problems. So I agree, I completely agree with that. So it's just a first step, and then when you make progress, when you understand better the first principles to improve solving combinatorial problems, then you can go to, as you said, much harder problems. Yes.
Another interesting research thing that's come up recently are quantum approaches. So quantum combinatoric searches, like quantum simulated annealing, where in theory, right, it can explore a much larger space in quantum parallelism, right? So in theory, these are unbeatable, but we don't have machines to run them yet. But that's another interesting way. The best machines I know of right now actually simulate the quantum machines. So you can simulate a quantum machine in a von Neumann machine and run a quantum algorithm on a simulated quantum machine and still get really good speedups. So
absolutely. Yeah. I think this is going to be very exciting because the main question is, which class of algorithms, you will be able to do. So this will basically make,
yes.
And this is, several, people now are trying to work in this direction. And so I haven't had time. So I wanted to touch, this topic, but I think it's a very exciting topic in the coming years as well. I agree. Yes.
Yeah, exactly. Unless you can write these quantum computers are not universal, right? So that you have to morph your problem to look like something they can solve. Yeah, it's not easy at all.
Absolutely. So I think, it depends on the structure of the problem. And once we are able to identify the structure of the problem, we can say, for example, if it can be done or not, or then we need, new architecture. But mathematics is here. So I think we have very nice years coming for research and interesting, projects. So it's going to be fun. Yeah.
Hi, I have a couple of questions actually. So one of them is, like you said, for the transform of the self-attention is O of n squared. So did you try the Nystrom based factorization that people have used now to make it down to linear to space and time?
Yeah, absolutely. So no, we haven't tried. So transformer is today, probably the favorite architecture for many applications. So people are developing, approximation of transformer with linear complexity, like the Nystrom technique. So that would be interesting to try, and see, what is the performance, and if the performance is good, then suddenly you can scale up, with linear complexity. You can scale up to some point because the GPU memory is going to be limited. So so even if you get to linear complexity, for your neural network for combinatorial optimization, you will still need, I think, additional ideas, like maybe doing some graph subsampling. I'm not sure, just getting the linear complexity is going to be enough, if you want to do TSP with 1 million, cities, for example. So I think that's very challenging, and it's going to be, very important to do it, if we want neural network to be able to compete with, existing very good solvers, because we know that the existing very good solvers, they cannot go to 1 million. So neural network, they should be able to go to 1 million, and because at some point, you have approximation. You cannot. Neural network is the science of approximation. So you want to be able to get good approximation where the standard, solvers has less, accuracy. But it's really an open question. Today we are not here. Traditional solvers like Concord are much better.
And my second question, I might have misunderstood. So there was a slide in which you have the decomposition of the probability distribution. And how are you decoding it? Is it via some kind of hidden Markov model?
Sorry, I didn't hear the beginning.
So there was a slide in which you have about decoding the probability distribution. So how are you decoding it? Is it via some hidden Markov model?
This one?
So this is a greedy search. There was another one. Where was it?
This one?
Yes, with this one, yes, the decoding.
Oh, yeah. Oh, yeah, sure. So when you train your neural network, you are actually training this probability.
Okay.
This probability is given to you. So what you do is that it's autoregressive. When you get the time t, you're already decoding the previous cities.
Okay,
so the neural network just predicts the next city. So this probability is given by your neural network, basically.
Oh, okay, I see.
Yes.
Okay. Thank you so much.
Sure. Thank you.
Hi, Dr. Branson. There's a question in the chat. Says super interesting research. Thank you for your presentation, and like to wonder about how adapt the temporal feature at your architecture, and just using transformer. I think that time is really important key at this task.
The temporal feature, not sure what they mean by temporal feature here. Maybe if
so maybe Tay, you might want to explain that.
Time probably maybe
scheduled.
Maybe it means the time constraints or the schedule constraints. So so these constraints can be added to the problem in a different ways. You can add these constraints in the objective. So for example, you can have a Lagrangian formulation of your objective, or you can also add this maybe at the decoding step when you do the search phase. So you have different ways to do that. Again, I think what is an advantage of neural network here is that it's more flexible, to add constraints to the objective than it is, for standard algorithms. So for standard solvers. So for standard solvers, so they are really good, if you want to do, if you want to optimize linear objective, quadratic objective with, polytope constraints. But if sometimes, you have more difficult constraints, then it's going to be much difficult to do, and you won't have like solvers that you can use directly. So with neural networks, you can design complex objective, and they will train. So solutions can be bad, solutions can be good, but I don't think it's something that they cannot do. It just you have more flexibility for, I would say, the objective you can optimize here.
Okay, any other questions? We have 4 minutes left, or anything folks want to discuss. Great. Again, I want to thank Dr. Bresson for the amazing presentation. And also I want to thank you for being a long-time collaborator and supporter of the DGL project. Really, on behalf of the DGL team, we really appreciate all the work that you've done by using DGL. Yeah, thank you again.
Thank you very much, Wenming. I mean, DGL was very important for us. So yeah, we really appreciate the work of the team, and it's very outstanding. Thank you so much.
Of course.
Also, if you have any suggestions for cuGraph improvements, please let me know also.
Oh yes. Oh, okay. So I can send you a list.
Okay, great. Yeah.
No, absolutely. I think there was so if we want graph neural networks to be successful, because now more and more people use GNN for their flexibility. Something that was a limitation was really the optimization of doing linear algebra, like sparse linear algebra for matrix multiplication, all of this. So I saw that you are working on that. Actually, you are improving the speed of sparse matrix multiplication. So if we want the success, so deep learning is basically 3 ingredients, right? We have algorithms, we have data, and then we have hardware. So if we want GNN to be successful, the hardware should also be should adapt to this specific structure. So I'm very happy your team is working on that. That's very welcome.
Thank you very much. Yeah, this is what we want to do, is try to get the best sparse linear algebra performance we can. it comes in handy all over the place, right?
Absolutely, I agree on that. It's not only graph neural network. Any graph machine learning techniques will be. I mean, it will leverage many of these techniques. Thank you so much.
All right. Anything else anyone would like to discuss? And I also want to bring Grace to. I want to thank Grace, my coordinator of the event, for spending a lot of time and a lot of work on this. And to thank you, Grace, for doing all the work.
Thank you.
And yeah, and also all the different teams that have been helping, especially the cuGraph team. So Joe, thank you for all the support and participation. And if anyone has any questions or want to reach out to us, definitely join us on the Slack channel. The Slack channel is quite easy to access if you have not done that already. And let me actually just copy that into the chat window. There you go. Find the chat window here. So I just pasted that into the chat window to everyone. So that is the Slack channel if you haven't joined. I know most of you have. So the other thing is that for MLSys, which is the conference that is at the intersection of machine learning and systems this year, which also features the GNN systems workshop on a Friday and Saturday of that week is over here. So feel free to register, and for students to register, I think it's about $25, and for everyone else, it's $100. And if you also would like to be a volunteer for the conference, feel free to reach out to me on Slack. So with that, I'll just thank everyone for attending our third workshop, and we'll see everyone next month. And if you need to reach me or reach anyone for anything, please definitely use the Slack channel as the default place. Thank you.
Thanks, Wenming.
Thank you, Wenming.
Thank you, Joe. Yeah, thanks, everybody.
Thank you.
Oh, Wenming, do we have the slides?